introduce Professor Andreas Fring. He studied physics at the Technische Universität München at the University of London. He received a PhD in theoretical physics from Imperial College London. He held postdoc positions at the Universidade de São Paulo in Brazil and the University of Wales in the UK. From 1994 to 2004, he was Wissenschaftlicher Mitarbeiter, I think that is research fellow, in the Department of Physics at the Freie Universität Berlin. He joined the City University of London and became a member of the Department of Mathematics in 2004, where he is now Professor of Mathematical Physics. His main research topics are integrable quantum field theories and quantum mechanics. He co-authored around 100 articles published in international journals and conference proceedings on topics including the form factor approach to integrable quantum field theories, factorized scattering theory, the thermodynamic bed ansatz, representation theory of Pseudo algebras, and Coxeter bio-reflection groups, high energy laser physics, pseudo-Hermitian quantum mechanics systems, and non-commutative space-time structures. Thank you very much, Professor Andreas, for coming to see the staff. You're a visitor now here in the staff, so please, the students, if you want to talk with Professor Andreas, you're in office. What is the office? The number of the office?
20.
20 in the P building. So, Mr. Clark, thank you. Thank you very much.
Thank you very much for the kind invitation. And yeah, if you want to discuss any of this afterwards, you just come to my office. So this is the topic. I will be talking about PT-symmetry in quantum and nonlinear systems. So this is an area which grew in recent years. I would say a little bit more about the history as well. And so my talk has 3 parts. The first one is an introduction, general introduction to the topic. I'm kind of assuming that you are not familiar with it, so I will introduce it to you. Then I will talk about nonlinear integrable systems, how to apply these ideas now in other areas. One idea is to apply it in your area, any area you work in. This can be applied, I can guarantee you. Yeah. And these are my areas of expertise, integrable systems, so naturally I try to apply it there. And also quantum field theory is one of my expertise, so I also try to implement these ideas there. So, yes? Yeah, sure. Sure. Okay. So yeah, I know how to do it. Okay. And then I share this like this.
Yeah, thank you.
It should be done now, yeah?
Yeah.
Okay.
Thank you.
Okay, so I remind you first, so all this is about non-Hermitian systems. So I remind you first, why are Hermitian systems useful in the first place? So if you take a standard quantum mechanics textbook, it will tell you a Hamiltonian to be physically meaningful has to be Hermitian. And I will convince you, hopefully, in this lecture, and if anything you take away from this lecture is that this is not necessarily the case. You can make perfectly well-defined quantum mechanical systems and other type of systems with non-Hermitian Hamiltonians, or even if you have a non-Hamiltonian system, this can be done. So why is symmetricity useful in the first place? Well, here's the little argument to show you that hermiticity ensures you the reality of energies. Yeah? So that's the first property you have that is ensured when you have an Hermitian Hamiltonian. And of course, energies need to be real, yeah, because that's what we measure. We measure real numbers. Your detectors don't show complex numbers. Yeah? So that reality is real, made up by real numbers. So if you have complex numbers, that's not a real system. Yeah, we can have complex energies, but that means you have decay. Yeah. And the other property that is guaranteed is the conservation of probability densities. So here I say
Yeah, thank you.
it should be done now, yeah?
Yeah.
Okay.
Thank you.
Okay, so I remind you first, so all this is about non-Hermitian systems. So I remind you first, why are Hermitian systems useful in the first place? So if you take a standard quantum mechanics textbook, it will tell you a Hamiltonian to be physically meaningful has to be Hermitian. And I will convince you, hopefully, in this lecture, and if anything you take away from this lecture is that this is not necessarily the case. You can make perfectly well-defined quantum mechanical systems and other type of systems with non-Hermitian Hamiltonians, or even if you have a non-Hamiltonian system, this can be done. So why is symmetricity useful in the first place? Well, here's the little argument to show you that Hermiticity ensures you the reality of energies. Yeah? So that's the first property you have. That is ensured when you have an Hermitian Hamiltonian. And of course, energies need to be real, because that's what we measure. We measure real numbers, your detectors don't show complex numbers. Yeah? So that reality is real, made up by real numbers. So if you have complex numbers, that's not a real system. Yeah? We can have complex energies, but that means you have decay. Yeah? And the other property that is guaranteed is the conservation of probability densities. So here I state evolving from time equals 0 to t by means of a standard evolution operator. And if I just sandwich it, then you see here that if my Hamiltonian is Hermitian, this just becomes 1. And the probability density at t equals 0 and any arbitrary time t is the same. So these are the two properties guaranteed by Hermiticity. Yeah. So usually when we have non-Hermitian systems, we think of dissipation. But dissipation means it has to dissipate somewhere, and usually you have an open system. That's not the type of systems I'm talking about. Yeah. So these systems are self-consistent descriptions with limitations of how much quantum mechanics is self-consistent itself. I will not discuss that. Yeah. I'm assuming here so quantum mechanics is a good description and self-consistent. And as I already said, both of these properties can also be achieved using non-Hermitian systems. Yeah. And you see here, this goes back, I explain this in a bit more detail, to an old paper by Wigner, from 1960, who showed this property here. If you take an operator O, that is left invariant on an antilinear involution, then and whose eigenfunctions are also eigenfunctions of the symmetry operator, then you have real eigenvalues. You have a real eigenvalue spectrum. And you see here, nothing is said in this statement about what O is. O could well be a non-Hermitian Hamiltonian. I explain this bit a little bit later. I just want to anticipate a little bit the result. And moreover, you can also define a new metric, that's the key here, and you have a self-consistent and well-defined quantum mechanical description. So even starting with this operator O, let's take it to be a non-Hermitian Hamiltonian, you can set up a well-defined quantum mechanical framework. And here are some key papers on the subject. Yeah, this is really where it all traces back to, but it hasn't really taken off. Yeah. And then here are some other papers. This is a key paper I will come back to again to show you how the area really became popular. Yeah. So many insights, your area is the same. Many insights have been found, but then they sort of get forgotten, and no one really picks it up. And eventually, someone discovers how important it is, and then it takes off. And this has happened with this paper here, 1998. And the reason is this. So here's the key observation in this paper. They have looked at this Hamiltonian, just the kinetic energy, p squared, and then here we have the harmonic oscillator, x squared, and deformed by some other terms, I x to the epsilon. And what they found is if epsilon is positive, so epsilon is this power here, here's the energy, your energy eigenspectrum is real. Yeah? Which is surprising initially, because if you, let's take epsilon equal 1, you have I x to the power 3, that's not an Hermitian Hamiltonian. Yeah? So according to sort of standard wisdom, more than 20 years ago, you would not have expected to find real eigenvalues. Yeah? So they were quite surprised to see that. And you can see here, I can vary epsilon for any value over here, and even, let's take epsilon equal to 2, you have minus x to the 4. You have an inverted potential, which you would, it's Hermitian, it's not complex, yeah, but you would still throw it away because it's not bounded from below, right? That's also a sick model, yeah, not because it's complex, but because there's no ground state in this model, yeah. But you see here, there's no difference, yeah, it's well behaved, and you can even take epsilon in between, yeah. So this was rather surprising. And here I mentioned already this point here, this is called the exceptional point. This is when two levels merge. Yeah? We know from Neumann, we know that if you have an energy spectrum, you parameterize by some parameter in your Hamiltonian, then these energy levels cannot cross. Yeah? This is forbidden level crossing. And here they do cross at this point into the complex plane. So if you have complex Hamiltonians, they do sort of cross, yeah, but they don't overlap in the real plane, that's forbidden, but they can come together and become complex conjugate. So that you can go further back in history, even to 1975, you can find an attempt to explain the hadron spectrum in terms of region field theory, and they do this with a non-Hermitian Hamiltonian. To my mind, all these old papers, they don't do it properly. So they're, in my opinion, not quite right. But they sort of stumbled naturally, this is the point I'm trying to make, in all kinds of areas. Very often you stumble naturally on a formulation that is not Hermitian. Yeah. And here are other examples. Quantum spin change, so in quantum metaphysics, you would be able to use that in quantum field theory. I will talk about it a bit more. In string theory, there are scenarios where you would like to have non-Hermitian Hamiltonians, but you don't even need a Hamiltonian. You could even start more abstractly from a deformed spacetime. Non-commutative quantum mechanics doesn't really deal a priori with Hamiltonians, but in that structure, you're also naturally led to non-Hermitian systems. I will not talk about it in detail here unless someone is interested. So, how to explain the spectrum? Let's see first, analyze and give some reason why we still have real eigenvalues. Yeah, and one argument goes under the name pseudo quasi-hermiticity. It's over here. Yeah. Here's the simple argument. We have now a non-Hermitian Hamiltonian. So capital H, I denote the non-Hermitian Hamiltonian. And small h is the Hermitian Hamiltonian. Yeah, and I've tried to find here a similarity transformation that maps the non-Hermitian Hamiltonian to an Hermitian one. Yeah, that's the key here. And then, of course, we know that the Hermitian Hamiltonian has real eigenvalues. I showed this to you already. But we know that similarity transformation don't destroy the eigenspectrum. And therefore, this capital H will also have Hermitian Hamiltonians, if I can find this transformation, yeah, and if that transformation is meaningful. Yeah. But the argument is simple. Yeah. So here is the argument. Yeah, I just have a new state now. So the eigenstates of my Hermitian Hamiltonian and my non-Hermitian Hamiltonian are just related by this eta. It has a name. It's called the Dyson map, because Dyson actually wrote this down first in 1956 already. It wasn't picked up, and he was a little bit dismissive about this. He said, "Oh, this is not practical. We cannot construct it." Yeah. But the key idea is already there. Here's some terminology. You can have different properties of these maps. Yeah. So this I didn't explain yet. So having found the similarity transformation, you can define a new map, rho, eta delta eta, and that is the metric. This object will play the role of the new metric. I will explain that. And you can have different properties for this role. So for a proper metric, it needs to be positive definite. And ideally, it's also inverse. It has also an inverse. It's invertible. And depending on which property you have, there's a different terminology, and you can draw different types of conclusions. This is technically it's not so important. Usually, we are dealing with this column, and we just assume that it's inverse, and it's also the metric is positive. So this kind of scenario is more interesting for mathematicians, and you can see Dieudonné, who coined the expression quasi-hermiticity. He was a mathematician. He didn't even assume that this rho is invertible. But that's just terminology. Now about PT-symmetry. So what is PT-symmetry? It's a simultaneous transformation in parity, in space.
Pues no habían mandado la liga hasta apenas.
And in addition, that's important.
Sí, de hecho está en presencial ahorita.
Está
en presencial, sí.
That is key. That makes it, I will explain that, an antilinear operator. Why is the I coming in? There are many ways to make it plausible. One is you take the commutator between x and p. X commutator p is equal to I. So if on the left-hand side I carry out the PT transformation, I pick up a minus sign from the x. And to compensate this, I need somehow something on the right-hand side. And that's guaranteed by the I. That's one way to make it plausible. There are other ways to look at it. So that's a PT transformation. And this I already mentioned. Because of this conjugation here, PT is an antilinear operator, meaning if I have a linear combination, I cannot just split it up, but when I do split it up, then also these coefficients are conjugated. And that property is now used to show that the spectrum of this Hamiltonian is indeed real. So if PT commutes with the Hamiltonian, if the eigenstates of the Hamiltonians are also eigenstates of the PT operator, and with the property that PT is antilinear, it is guaranteed that the energies of the Hamiltonian are real. Or any other operator. I took it here to be the Hamiltonian, but it could be any other operator. So here's the little proof. It's just one line. You start with the eigenvalue equation, and I'm just using these three properties here. And you see here the outcome is that if I have these properties guaranteed, then the energies are in fact real. And you see here, I did not use at all that the operator has to be the Hamiltonian. It just has to have an eigenvalue equation of this type. And also, that's also important, I didn't really use this representation of PT-symmetry. I just used the fact that this is an antilinear operator. We usually call it PT because that's sort of less formal as an antilinear operator, but we mean PT in a general sense. All you need is any type of antilinear transformation, and you can go through this argument and it will hold. I never used the fact that this is an actual realization. And in fact, in higher dimensional systems, this realization needs to be modified. So what happens if I weaken some of these properties? One way to weaken the properties is to give up the fact that the eigenstates of the Hamiltonians are also eigenstates of the PT operator. So if this is broken, but still my Hamiltonian is PT-symmetric, what happens? So instead of PT acting on phi1 giving phi1, it gives just somehow the state. I call it phi2. And each of these eigenstates will have an eigenvalue equation, and they are related. So here's the relation, here's the little argument that shows you if I give up this property here on top, then the eigenvalues become complex conjugate to each other. That's the other scenario. So, and the point when this happens, this has a special name. This is the exceptional point. I mentioned that already. So, and also this, I stress again, PT is just an example of an antilinear operator. It can be any other antilinear operator. So this is the general picture you have. Here's the PT regime. You have real eigenvalues, and then they join up here, and they become complex conjugate. The dotted line is the imaginary part. They share the real part, still the eigenvalues, but they also now have complex conjugate parts. That's the question.
May I ask a question?
Sure, of course. Please, everybody, ask a question if you.
I think I understand what spontaneous breaking means in the context of quantum theory, but what are you referring to in the context of general quantum mechanics?
Yeah, that's a slight misuse of terminology. It's not spontaneously broken in the sense of gauge theories and so on. People introduce this language here, but I told you precisely what it means. What it means is that the eigenstates are no longer eigenstates of the PT operator. That's what it means. So, but this is terminology now commonly used in the broken PT regime. Some people just use broken PT regime, and some people use spontaneously broken. This is slightly misleading, I agree. So that's the picture one should have in mind. And here's another. This is not a fundamental explanation, but this is just a feature. That goes under the name supersymmetry. It's an analog to standard supersymmetry in particle physics, which is used in quantum mechanics. Mathematicians call these Darboux transformations. But the key is that you have two Hamiltonians here that are isospectral to each other, which is what we had before. We had the Hermitian and the non-Hermitian Hamiltonian, and they were isospectral to each other. And here you also have H plus and H minus. They're constructed like this in terms of these two differential operators, and they differ just by this sign. And one can easily show that they have the same spectrum, except usually you lose the ground state, but that's not that important. The key in this context is that we can achieve that one of them, one of these Hamiltonians is non-Hermitian, and the other one is Hermitian. And the condition for this is that the real part of this function here is called the supersymmetric potential is equal to a half the logarithmic derivative of the imaginary part. Superpotential. But this is just a feature. This is not a fundamental explanation. This is more pseudo-hermiticity and the PT argument. This is really something you can use to show that a system has real eigenvalues. Okay, so this was the spectral analysis. This will guarantee you and explain to you why the spectrum is real. And we also want to set up now a consistent quantum mechanical framework. And I want to show you how to do that. So you need to ensure you have orthogonal eigenstates. So for a start, if you take the non-Hermitian Hamiltonian, you calculate the eigenstates, they are not orthonormal to each other because they are indefinite. They don't, if you just take them straight away, they don't give you an orthonormal system. So we have to construct it. We need to define what we mean by our physics, namely what are our observables, and there's a question: is this construction unique? And then more technical, how to actually do this. So first argument, here's the simple argument you can find in any textbook that guarantees you orthonormality of your states if your Hamiltonian is Hermitian. So Hermiticity means here a dissymmetry relation. That I can pull my Hamiltonian from the left to the right if you like. And you can see here easily that if so if n is equal to m, then we guarantee that the energies are real, and if n is not equal to m, then we have that these states are orthogonal to each other, or orthogonal and then are normalized and so on. And now we can show. Now, if I redefine my inner product now, so this was used here. We had the standard inner product. I put here an eta square, and remember, eta was this similarity transformation. And if I put this object in here, then a simple argument you can show. Actually, I'm assuming here that eta is Hermitian. This was this object rho, which in general is eta dagger eta. If I put this object here, then with respect to this new inner product, this non-Hermitian, originally non-Hermitian Hamiltonian in this standard inner product becomes Hermitian. I can move it from the left to the right. Yeah. This is an identity now in this new inner product. That's the key. Yeah. And here's a little argument. I will not go through it in detail. You can easily show this, that indeed, just using these properties here, that this Hamiltonian is related by similarity transformation. Here's the argument. You can show that with regard to the new inner product, this originally non-Hermitian Hamiltonian becomes Hermitian. And then we can recall just the argument I showed you for the Hermitian Hamiltonian, and we can now guarantee that the eigenvalues are also real for this. Yeah, I showed this to you from a spectral analysis, but this also follows now from this argument. Yeah. And moreover, the eigenstates are orthogonal. That's what we want for a proper quantum mechanical system. Yeah. So what are the observables? Well, observables are self-adjoint or Hermitian operators. They have precisely this property. Yeah. The Hamiltonian is one of them, has this property. I can move it from one side to the other side. And we don't worry here about domain properties and so on. That's technical. We have to think about how these operators are defined on the left and on the right, etc., on the domain of these spaces here. Yeah. But this is the key. These objects are observables. Yeah. So in the non-Hermitian system, the old variables are no longer observable. Yeah. So if this is if you think of the example, p squared plus ix to the power 3, the p and the x, yeah, which would correspond to the small objects here, they are not observable in the non-Hermitian system. But they have to be related in the same way as the Hamiltonians. Yeah. So the observables are different types of objects. Yeah. And this is just what I said for this example. So this capital X is observable, and this capital P is now observable in your non. So one should be careful when one talks about the physics now in this non-Hermitian system. The measurable quantities are different. Now, how to solve this? Well, I showed you already all the equations. Yeah. So if we want a metric, we can solve the similarity relation here. And then we construct eta dagger. That's easy to do. Multiply this out, and then we have a metric. Yeah. And then we can check some properties. Is the metric positive, definite, and so on. This we should also ensure. Yeah. The other way is we just conjugate this equation. This is the quasi-hermiticity relation. We conjugate this, and if I'm also interested in the Hermitian counterpart, then I could try to take the square root here, which is slightly more complicated, but can be done sometimes. Yeah. In general, to do this, it looks easy, but in general, it involves complicated commutation relations, and even for the simple model, the ix to the power 3, this is only non-perturbative. But it can be done. Some solutions can be found exactly. A nice example is minus x to the 4, the one I showed you. There's an exact Dyson map or metric known in this case, non-perturbative, and this is even now measured in laboratories. Yeah. So this particular one also minus x to the 6, minus x to the 8. So this whole series in the laboratory in Yale, they're making our experiments, just confirming this. Yeah. Yes.
I have a question.
Yes.
Okay. I need the microphone. In the previous slide, you talked about the observable.
Mm-hmm.
What is the meaning of this new X, capital F and capital P? Is the same as in the Hermitian system?
So if small o, so the original example was h, small h, which was the energy, yeah, in the non-Hermitian system, this is the energy, the non-Hermitian Hamiltonian. If was the observable in the Hermitian system, then capital X is the corresponding coordinate in the non-Hermitian system.
Okay, so
That's the interpretation.
direct.
It's a direct, it's not something new. Yeah, that was what you're aiming at. Okay.
Okay,
Yeah, it's direct. Yeah.
thank you.
Maybe I can mention that at this point already. Yeah. So these maps, these constructions are not unique. Yeah. And that's a kind of a problem because your physics becomes a little bit arbitrary. Yeah. We are used to the fact I give you a Hamiltonian and then all your physics is defined. Yeah. But what you are doing is when I give you a Hamiltonian, you also implicitly choose an inner product. You make a choice. It seems very natural, and there's one choice you make, yeah, namely this standard choice. Yeah? And this is not what you do in the non-Hermitian case. In the non-Hermitian case, you need to construct the inner product, and that's not unique. Yeah? And from what I just told you, if I take here a different map, then I get a different observable. Yeah? So there's a way to make it unique. Yeah, that's already done in this paper. They already thought about it and noticed the date, 1992, before the Bender-Böttcher paper. They already noticed this ambiguity. There's lots they did not understand, yeah, but this aspect they understood about the uniqueness. And you can make it unique by picking another observable. If you say, I want this operator to be an observable beside my Hamiltonian, or any two, then your metric is unique. Yeah, that's the way to make it unique. Yeah. Okay, so this is about the spectrum, the quantum mechanical framework, and here's a little disclaimer, yeah, just to say this is not a new type of quantum mechanics. Yeah, sometimes this is portrayed like this. This is standard, old-fashioned quantum mechanics, except you are giving up the restriction that the Hamiltonian has to be Hermitian. That is not a necessary requirement. So it's enlarging the scope. And there's another question.
Yeah, sorry. I've now understood what's the kind of your metric. For example, if you say that this metric is about the geometrical difference or relativity, special general relativity, or what kind of metric is that?
This is quantum mechanics. This is not general relativity. Yeah, and you have a different type of metric in mind. Yeah, this is just defining an inner product. That's all.
Okay.
Yeah. That's all it is. Yeah. Okay. So here's an example just to illustrate all the features you can reproduce here. Simple 2x2 matrix Hamiltonian in terms of Pauli matrices. You can all work out the eigenenergies and the eigenspectrum. And here's the typical feature. Yeah, there's a square root. And to guarantee the eigenvalues to be real, modulus of lambda has to be larger than modulus of kappa. And if you go to this point, you have lambda equal to kappa. We have the exceptional point. The eigenvectors in this case coincide, they coalesce, people say. And if you go beyond, you also see the feature, they are complex conjugate to each other. You have two eigenvalues and they're complex conjugate to each other. And you can also see this property here, that the eigenstate is an eigenstate, the eigenstate of the Hamiltonian is an eigenstate of the PT operator. Yeah. So here's the PT-symmetry in this case. You can realize it by sigma z. It's just 1 minus 1 and the complex conjugation. And you can see here, if you act on this, we pick up a minus from the sigma coming multiplying the lower entry, and we pick up another minus from the conjugation. So this is an eigenstate. Yeah. And this is no longer true when we are in the broken regime or spontaneously broken, as some people say. Then here we pick up an I, and this is no longer true. Yeah. So all these features, which I explained to you, you can see here in this simple example, 2x2 matrix Hamiltonian. And the claim is, this is also far time independent. If you switch on time, then actually this regime becomes also physical, which is very nice. And that's why I personally believe time-dependent systems are very interesting. Here's another one, infinite dimensional Hilbert space. Is two harmonic oscillators coupled to each other in a PT-symmetric fashion. They're coupled in the X and the P's, and there's an I, which makes it PT-symmetric. And PT-symmetry here, or more generally, the antilinear symmetry, is realized like this. Notice I'm not reversing all space, not X and Y goes to minus, because that would not be symmetry. You see this here, I picked out minus minus, so it's plus, but there would be minus from the I. That's not PT-symmetry. So, but this is, this is a PT-symmetry, and this PT-symmetry guarantees you again all the features I explained before. And the corresponding Hermitian counterpart is just a combination of harmonic oscillators in X and Y. And here also you can see the feature that once you come to this exceptional point, this symmetry or this transformation breaks down. It becomes ill-defined. That's typical. That you can see this exceptional point either in the spectrum or in the actual transformation. That has to go one to one. What happens when you switch on time? I already said this is very interesting. So think about the Stark Hamiltonian or so, some time-dependent Hamiltonian. That's the physical motivation for looking at these kind of systems. They have their respective time-dependent Schrödinger equations. And again, we assume this relation between the two eigenfunctions or solutions of these equations, but now eta is time-dependent. And then this is, when I just plug this in here, this is now the relation between the two. If you notice here, this capital H is no longer pseudo-Hermitian, which means related by similarity transformation to the small h, because there's this additional term which only vanishes when the metric is time independent. And that means that this object, capital H, is no longer observable. So there's now a distinction between the Hamiltonian, which is the object that satisfies the time-dependent Schrödinger equation and guarantees the evolution of the system, and the observable energy. The observable energy must now be newly defined. So here's the other equation. There was this quasi-Hermiticity relation which conjugates this involving the metric, and there's also correction. So this is just what I said. The energy operator has to be now redefined. This is now the energy, not this capital H. And that caused a bit of controversy, but most people accept this now. This is the resolution of this puzzle. This duality property a Hamiltonian usually has, as solving the Schrödinger equation and being the energy operator, is now split. There's a different type of operator being the observable energy. Because that operator is related by a similarity transformation to the small h. Okay, some applications. Big application is in optics. The reason is that the paraxial approximation of the Helmholtz equation, which is written here, looks formally equivalent to the Schrödinger equation if you identify Z with T. And Nature Physics declared in 2015 that the applications in optics are amongst the top 10 discoveries in the last 10 years, between 2005 and 2015. So this is a huge field now. So there are optical experiments all over the world making use of these ideas. And so what about these time-dependent systems? I just want to show you and convince you that the time-dependent systems are interesting and give rise to new physics. So here's a solution for a time-dependent system. I don't want to go into details. So it's the same Hamiltonian we had before, two harmonic oscillators coupled to each other, but now with time-dependent coefficients. And this system is nice because you can express this in terms of its case, which satisfies a Lie algebra, and you can solve this in a systematic way. So it can be solved, it's parameterized elegantly in terms of this, what is called the dissipative Emakov-Pini equation. Emakov-Pini equation is one of the simplest and nicest nonlinear equations. You see here is nonlinear. It was an x to the power 3, which can be solved. So how this is done is another story. I don't want to go into details. There are lots of techniques to deal with this, but you can imagine it's many degrees more complicated than time-independent case, because you have to satisfy now also differential equations for these time-dependent coefficients within the Dyson map or the metric. The statement is, if now you do this and you calculate the instantaneous energies, which before I showed you the explicit argument or complex conjugate, they are now real and are completely physical. And therefore are physical. And some application, now one can think, well, that one should look at now some concrete physical systems and see what other physical quantities do when they are subjected to this kind of setting. And one is, one can calculate Neumann for Neumann energies, one can formulate this in a non-Hermitian system as well. And the typical behavior you expect is what is called the sudden death. It's a very rapid decay of the entanglement or the entropy, instead of an asymptotic decay. And if you look at this in the PT regime, which in general behaves in the same way as the Hermitian system, we observe this. This is a rapid decay. So this is, we'll not describe the model in detail. This is just one photon cut into a bath. And this N here is the size of the bath. The key is here, we have here a sudden death, a rapid decay, sudden death, as it was called in this paper I showed you. And this changes slightly when you change the size of the bath, but it remains that feature. And there's a revival because there's an oscillation. That's not the new feature, the revival. The new feature is this. We can now calculate the same thing at the exceptional point, and this is not a rapid, and this is more asymptotic, and even more interesting, when we go to the broken regime, we reach a finite value. So this is different types of physics, depending on which regime you are in. And there are three regimes. This exceptional point is a regime in itself. And more details can be found here on this part of the talk, based on a virtual meeting held here in Mexico. And I understand the proceeding of this is coming out soon. I just got a confirmation. Alternatively, you can also look at, there's a book. This is now an old area already, 20 years old. So we wrote a book on this subject. Carl Bender, the founding father of this area in a way, wrote a major part, but there are different types of contributions from different authors. So, new topic, second part of my talk. What about applications now in other areas? And integrable systems, I told you, is one of my passions. I like integrable quantum and classical systems. So how can we apply this there? What can we do with these principles? So here's probably the prototype integrable system, which is the KdV equation. And what I want to do now is just have a look what happens when we use a complex field. It's actually not how I started to think about it. Usually you want to find something new. So this I will not talk about, but you can find it in the book. You can think of deformations, PT-symmetric deformations of this system, just as the ix to the power 3 was a deformation of the x of the harmonic oscillator. Sadly, when you do this, most of these systems, they lose the nice property of being integrable. But this is actually easier to first think about the complex KdV equation. So I think this is the easiest example to explain things. And you can think of this as a coupled system as well. And you can easily see, this system is not entirely new. For some special cases, if you drop some of these terms, you get well-known integrable systems out of this. yeah, which are sort of coupled systems. And this is the PT symmetry how it's realized, straightforward way. And moreover, you can construct the lax pair. This is the known lax pair for the real case. You can still use this lax pair for the complex case, and therefore your system is still guaranteed to be integrable. How to solve it? Well, usually you solve it, this is one method to solve this type of nonlinear equations. You bilinearize it. If you haven't seen this before, I cannot explain it quickly in 2 minutes. But the idea is you reformulate the system. This is a transformation of the original U fields, and these are what is called Hirota derivatives. And this is again just a new formulation of the KdV equation. It's equivalent. And this formulation guarantees you that you can now, order by order, I'm plugging in now for this tau, this expansion, and it looks like a perturbation theory, but the key here is it's not a perturbation theory. If I take this as the first order, what you get is a one-soliton solution. If you go to the next order, you get a two-soliton solution. So this series is not perturbative, this is exact, depending on how many terms you include. And the reason for this is this reformulation. So if you don't know it, don't worry, but it can be solved. And there are other methods to do this, which I will not explain. So here's the solution, just to explain to you. This is how we got a solution. So now this solution is complex. It has a real and an imaginary part, and it's PT-symmetric. You can see here, if you send x and t to minus, then the cosh will not pick up a sign. Here's a sinh, which will pick up a minus sign, but there's the I. So this solution is also PT-symmetric. And here's the plot. The one-soliton just looks more or less like a normal soliton, but it has this little wings here, but everything is known, and there's now also an imaginary part. So everything is known explicitly. And they depend on this parameter over here, I theta. And we can now calculate for this solution, for instance, we can calculate the conserved charges. In particular, we are interested in the energy, in the momentum, and the mass, and you can just compute this exactly. And even higher charges, where we don't really have a concrete interpretation what they might be, but there's a close formula you can use and calculate. Now, the key question here is, as in the quantum mechanical scenario, why are energies real? That's the first question, because we want real energies. And indeed, they are, and this is a simple argument here. If I have this property on the Hamiltonian, then the energies can be guaranteed to be real. In this case as well, they are defined as this integral. However, if I take these solutions, which I had here, just the one-soliton is already nice. If I take this solution and I make this parameter now here, not just purely imaginary, but just complex. So if I say this parameter now has a real part, then the PT symmetry is broken. What happens in this case? In this case, if I do this, so this is the parameter, I'm putting here now a kappa also in this parameter in the solution, but I can absorb this into, here's an integral in x, I can just absorb this into the limits of the integration by a shift. And then it's PT-symmetric again. Or alternatively, I can, because this is these are quantities preserved in time, they are conserved charges, so this is true for all time, I can make a shift in t as well and absorb it, and then I can use the old argument again, and by PT symmetry, which is this property here, the energy is guaranteed to be real. But what about when I have n larger than 2? So I did not explain you yet. When I go and construct the two solitons, you get 2 of these parameters. So let's call this alpha 1. For the two soliton, you have an alpha 2, an alpha 3, and alpha 4, etc. So because it's very technical, but in this approach, we have all the solutions I showed you. But doesn't matter. We have all the solutions. So I have an N-Soliton solution that has now n parameters. So if I take a two-soliton and I break the symmetry, I can absorb one of the shifts in X and one of the shifts in T. And I still can use the fact that it's then PT-symmetric. But what about 3? If I have now 3 really complex numbers, then I broke the symmetry and I have only 2 ways to shift it. There's no way anymore to guarantee the reality using these arguments. And so somehow we were puzzled because PT-symmetry no longer guarantees the reality of multi-solitons. It does it for one-soliton, two-soliton, but not for a three-soliton. How is that possible? And we calculate it, and it's real numerically. Actually, even analytically, you can calculate. So what is the argument? How does it work? And the argument is integrability, because asymptotically, if you have a multi-soliton, this is the key property of soliton scattering. You have a multi-soliton, and they scatter, and then they regain their shape. They scatter up to a time shift or a displacement, whichever way you want to look at it. And then asymptotically, they separate into one-solitons. But for one-soliton, I showed you how the reality is guaranteed, and then you can use, again, that argument. So asymptotically, and the energy doesn't change, so I can calculate it in the asymptotic regime. So to guarantee reality, we need here PT-symmetry and integrability. So this is the novelty that we also have to imply and use integrability. Okay, so this is the statement here. This is the reality condition. This guarantees real energies. Moreover, so this is now a new idea, can we construct some new models? So this is a nice construction of getting new systems out of using PT-symmetry. So here's an example. So it's a nonlinear Schrödinger equation, and it's extended, if you like. This is the nonlinear Schrödinger equation. It's extended by higher powers, and you can think of this extension, as the PT-symmetric extension. You see here, this term is PT-symmetric. You send x to minus x, and the minus sign is compensated by this I here. The same from this term and the same from this term, if the alpha, beta, gammas are real. So this is a PT-symmetric extension, and in fact, these systems are known. Depending on the ratios of these parameters, they can be found in the literature. So 163, for instance, the Sazen-Satsuma equation, it's known to be an integrable system. And here I'm interested in this ratio 160. We're setting this part to 0, and that's called the Hirota equation. So this is the system I want to look at now. And here's the formulation of this system in terms of the zero curvature condition, which guarantees you, similar as the Lex pair, the integrability. And what you end up with is these 2 sets of equations, where the R and the Q are these off-diagonal entries. And the standard way to look at this system, to make this compatible, is to assume that R is the complex conjugate of Q. This kappa here is just a plus minus sign, could be plus or minus as well. And if you do this, then one of the equations just becomes the complex conjugate of the other equation, and therefore you have reduced your system to just one equation. That's the standard way to look at it. But that's not the only way to look at it. You can also make a different choice and take R of x and t to be the parity conjugate of this field. And what that means is I'm also changing x to minus x. So I'm introducing a new field. And if you do this, the equations, I also have to manipulate a bit the constant here, then this second equation becomes the parity conjugate now of the first equation. And again, you have only one equation, but it's integrable by construction. Yeah. And moreover, it has now two types of fields. Yeah. So I'm calling now these fields which have minus x, I call them q tilde. And you have now one equation here, and they involve q's and q tildes. So they involve fields at x and fields at minus x. That's very interesting because they're non-local in the sense that they have now fields being at different positions in x. And you can, of course, you can imagine now there are more options. I can also make this choice and take it to be the time conjugate, the r, and all the other options are also possible. Really PT conjugate, changing x to minus and t also to minus, and all the other options. Yeah. And all these systems have quite different behavior. Yeah. It looks almost the same, but they are behaving in a quite different way. Yeah. So I'm focusing on the PT conjugate system, and here is the standard formulation for this system. It's again using the Hilbert bilinear form. If you don't know it, don't worry. Yeah, it reduces to solving these two equations in this apparently perturbative way. But now we have two solutions to solve. For the KDB, there was only one field. Now we have two fields. And again, you get exact one-soliton solutions. Yeah. Now, in the non-local case, there's a problem because if you read off the equations you get, this is not bilinear. Yeah, so bilinear means there are only two of these fields, G and F. Yeah. So one needs to enlarge the techniques, and we managed to do that. This is the trick. We make a new assumption, we introduce a new field, H, and that field H satisfies this equation, and then you can cancel out one of these factors. And this equation becomes bilinear, and the price we have to pay is we have to introduce a new field and we have to solve a new equation. Yeah. But this also opens up new possibilities. So here's a solution. This is the one-soliton solution. This is the system you have to solve. Don't worry about the details. And we get out a solution. Yeah. Where this epsilon is a former parameter that we set to 1. Yeah. But now we have new options as well, because we set it to 1 anyway. So here we can solve these 6 equations, all these coefficient equations. So there are 6 equations we solve. But we can also try to set this to 1 beforehand. This equation didn't exist before involving the H's. Yeah. And that gives rise to a new solution. And you see here, this is quite different. Yeah, this is a rogue wave solution we get out in this case. So now here, the epsilons have been set to 1 already, and we get this solution. So this is much richer. You get new types of solutions, and yeah, it's a new type of integral systems we got out of this principle of using PT-symmetry. And you can go to Two-solitons. Here's the solution. Don't worry about the details. Here's the plot. Yeah, you can find exact solutions, and you can go to any order you want. Yeah. So next question is, are these solutions very artificial? Are they stable? Yeah. So if you find solutions to these systems and you perturb them a little bit and they go off, then these are usually not good solutions. They're not physical solutions because they decay under the slightest perturbation. So we looked at stability of these systems, and here are the key features of the stability analysis. If I just do this in general for Lagrangian of this type, this is then the equation of motion, and we introduce a little perturbation, chi. Then chi satisfies this. If I stop this, this is now real perturbation theory. I'm stopping at order epsilon squared. And if now I want this to be stable, this is the original solution, I want this to vanish. So we make an ansatz of this type. I take chi to be e to the I lambda t, phi just of x. We take a factorization, and then we solve this. We solve this Sturm-Liouville problem. This again, we are having our Schrödinger equation here, and we can attempt to solve it. And if lambda is real, that means we have only introduced here a little oscillation. But if lambda becomes complex, then we think of this as an unstable solution, because it can just go to infinity. So that's the setup, yeah, and the complete system. We look at this, the Bulov dot model. This is interesting for many reasons, because it's exactly integrable. The S matrix in the quantum field theory is exactly known. There's one particle that fuses to each other. I repeat that, the S matrix is known exactly to all orders in perturbation theory. That's very unusual, but this can be done for this system. So this is also interesting, therefore, to see classical aspects we haven't looked at before. So here's the corresponding Euler-Lagrange equation. And these are solutions to the Euler-Lagrange equation. And they have various features. Maybe I don't go into detail, yeah, but they are complex. That's what we had before. Different types depending on the parameter k here. They can be of this type or the previous type I showed you. They can be of breather type. This is more or less like a breather type. And they have, of course, an imaginary part. They're complex. And so for this type of solutions, we want to now solve the Sturm-Liouville problem. And the Sturm-Liouville problem for the one-soliton solution looks like this. This is the potential. I remind you where the potential comes from. So the potential is coming from here, down over here. Yeah, we have to plug in now into the potential, the solution, and take the second derivative. And that's then the potential of the Sturm-Liouville. And what we find is this potential, which doesn't look nice, yeah? But I showed you before in a completely different context these Darboux transformations. And it turns out that when you Darboux transform this potential, you get the partner potential, which is very well known. It's the sec squared potential. You can find it in Landau-Lifshitz. There's a solution for this potential. And then we just translate it back using the Darboux transformation. And the solution has lambda, in this case, that was the parameter we were interested in, is real 3/2. Yeah. So that means the solution is stable. And similarly, for the other type of solution, we can do this analysis, and we always find the solutions are stable. And also, for the system I showed you before, I deliberately didn't pick that analysis because there the stability analysis is a bit more complicated, but also the non-local solutions, which I showed you before, they're also stable. Yeah. So these are interesting systems also from a physical point of view. So they have two key features physical systems have. They have real energies, the solutions, and they are stable. So another topic, when should I stop? How much time do I have left?
Let's say, yeah, you're gonna question. Let's say 5-10 minutes.
5-10 minutes, okay.
So on the last topic that you discussed, we follow that model or whatever.
Yeah.
In case the field phi is not real but complex,
Yeah.
then you would have parity in addition, and this can be very interesting.
We have parity.
C parity. I mean,
C parity.
Between particle and non-particles.
No, because the Bulov dot model has. Oh, you mean then they're complex quantities? You are right. Yeah, I agree. Yes. Then we can think of two particles. You are right.
So has it been studied?
No. There are many open questions. So, but I will now come to field theory. Yeah? So I deliberately didn't think of C parity because so far in quantum mechanics C doesn't exist anyway. So here's in 5 minutes quantum field theoretical applications. This is the motivation. There are lots of shortcomings in a standard model. And therefore you're looking for alternatives. And in particular, in the Higgs sector, we can use a lot of these ideas. So I will not discuss the shortcomings and so on. but an expert in this field is John Ellis from King's College. He also thinks very much that these are interesting ideas. He keeps writing papers on this as well to explore different sectors. And these days, the Higgs sector is in particular very interesting. So that's what we are looking at. We're looking at the Higgs sector in the standard model. Yeah. Meaning, we are looking at sort of actions of this type, where now these fields are complex. But there's a problem with complex systems. They are actually incompatible, because we can have two different scenarios now when we vary these actions. Namely, we can vary with respect to the real fields and the complex fields. And that gives different answers. And one way out is to keep surface terms, meaning your integrals or your fields are not assumed to vanish at infinity, and you keep them. We find this very artificial, and for everything I told you in this talk before, it seems more natural to look also in the field theory for these similarity transformations. And that's a different type of approach. I think these people realize also now that this is fairly artificial and cannot always be used. But there are alternatives. That's all I'm trying to say. So the key findings here, so we look at the Goldstone theorem and we look at the Higgs mechanism. And the key findings, I already anticipate this here, and I explain it in a bit, not too many details because of time. So the Goldstone theorem holds in the PT-symmetric regime. It is broken, or it's no longer valid in the broken regime. And at the exceptional point, the Goldstone boson can be identified, but at the zero exceptional point, it cannot be identified. What is the zero exceptional point? That's the point where the eigenvalue is zero, which usually you don't look at, but here we encounter this in a very natural way, and this gives rise to a new phenomenon. Well, then we look at the Higgs mechanism, which is the mechanism that gives mass to the Goldstone boson. And again, we find it works in the PT-symmetric regime. It does not work in the broken regime. And the Goldstone boson remains massless at the zero exceptional point, which means also there it breaks down. Yeah. So let's have a closer look. Here's the little argument I remind you about the standard Goldstone theorem. So we have our vacuum defined in this way, the first order term vanishing of the potential with regard to the first derivative, and that defines your vacuum. And now we're looking at the symmetry. We're shifting the field by some symmetry, usually gauge group. And then if this term now is zero, that's this term, then we actually have a symmetry. That actually means we have a symmetry. And therefore we have we can deal with this equation. And now just a little trick. I'll differentiate this equation now with respect to phi j and evaluate it at the vacuum. So this is easy, just the product rule, and you get this expression. But here we have again the vacuum, which is zero. So this term cancels out, and what you're left with is this equation. And you recognize here, this is the Hessian, and the Hessian is the mass matrix, or the squared mass matrix. So this is the first order term, this is the Hessian. So I write it down here. So this is the equation. This is the Hessian, which I replace now as m squared times this symmetry differential. And now we have two options. We have the option that actually we have a symmetry here for the vacuum. Namely this delta phi I at the vacuum is zero, and then there's no restriction on m squared. But if the symmetry is broken, so meaning this is not zero at the vacuum, we have a solution that is not symmetric, then we must have zero here in m squared, so m squared has a zero eigenvalue. That's the Higgs factor, that's the Goldstone boson. This zero mass solution is the Goldstone boson. So what about the non-Hermitian version? In the non-Hermitian version, we pick up here some other factor, which makes this mass matrix no longer Hermitian. And here's an explicit example. So it's a theory that is abelian, so it has an abelian symmetry here with the properties. So here it's just an abelian one symmetry we start with. We have extended this to ST2, etc. But the easiest one first to see what happens is a U1 symmetry. It is now PT-symmetric, but modified. You see, this is not standard CPT symmetry. There are these factors coming from. That's why we call them modified. And we do not expect to find CPT symmetry because this is a non-Hermitian theory. So these are now the properties, and these C's are just plus minus signs. So it's a field. There are three complex scalar fields. And these are the symmetry properties. Let's work out the equations of motions. And I told you they are not compatible in non-Hermitian theory. And here are all the 6 equations of motions you get from all these fields. And you can see here, I vary with respect to phi 1, phi 2, phi 3, and I vary also with phi 1 conjugate, phi 2 conjugate, and phi 3 conjugate. And this is what you get out. And you see here, this equation should be compatible with this one, but it's not the complex conjugate because of these terms. There's a minus sign, and the C's are real. And so is this equation not compatible with this one because of these minus signs here. And also here, this green term spoils the compatibility. So this is a general problem if you have non-Hermitian theories and you vary. But this is rectified by looking again at the similarity transformations. And now these are now equal time commutators we have to use instead of just commuting our p's and x's. And this one is very simple. It will just act like this. So it will introduce i's in the right place where we need them. So here you saw there are some i's maybe missing. And this is exactly what happens. This becomes now compatible. And here I also split up this field into real and imaginary parts. So I'm just dealing now with real fields. And then we have here these 6 equations of motions, which are perfectly well defined. And now we're looking at the system, and we analyze now the mass matrix or the mass squared matrix, and which I told you is just the Hessian. And then we have the Goldstone boson, which is just not coming out here yet because this is now first for an invariant vacuum. We have no Goldstone boson, and if we take this more complicated vacuum, which is SU1 broken, then we get 1, 0 eigenvalue of m squared, which is the Goldstone boson. So that's what's happening. How about non-abelian theories? So this is now a non-abelian theory. We have here an SUN symmetry, and the same thing happens. And this is now the interesting picture that summarizes the findings. So there are different C's with plus minus signs. We can take them in different combination: 1 minus 1, minus 1 1, and 1 1 minus 1 minus 1. That is well defined. But these two theories, these two choices, give rise to interesting pictures. And this orange region is the PT regime, where everything works well. And then on this axis, there are these ratios of these masses, these mass parameters. And what we typically find then here is a boundary regime. This is the exceptional point. And this dotted line is the 0 exceptional point. So that's an exceptional point, which is eigenvalue, which is somehow very special and not like the rest of the exceptional points. And so in the physical regime, we find the expected number of Goldstone bosons. So the Goldstone theorem works. At the trivial vacuum, we find no Goldstone boson, which is also expected. At the standard exceptional point, we also find the expected number of Goldstone bosons, but this needs to be treated separately. The exceptional point can in no circumstance, even for matrix models, be treated in the same way as the PT regime. Yeah, just think again about the quantum mechanical model and think of the exceptional point. For the matrix model, you get a non-trivial Jordan form, yeah, of the matrix, and you have to diagonalize this system separately. And that's the same over here. You need to treat this separately. And the interesting point is the zero exceptional point as well. It is not possible to actually construct the Goldstone boson in this case. So therefore, the Goldstone boson at this point breaks down. So that's the most interesting point here. Now the Higgs mechanism, which is the mechanism that gives now the Goldstone boson a mass. So we replace all derivatives via minimal coupling in this way, and I will speed up a little. And again, what we already found for the Goldstone boson is reflected now at the Higgs mechanism. Yeah. So in all these regimes, I told you where the Goldstone boson can be obtained, we can also make it vanish using the Higgs mechanism. Yeah. Except at the zero exception. That's where it breaks down. So I will stop here. And there are some interesting, if you are interested in this area, there's an interesting proceeding we published very recently with new results and all sorts of areas. And if you're interested, we also have an online seminar that runs every second week. It's fairly popular. Tomorrow is a talk. Tomorrow might not be the best one to join. I'm very skeptical that this actually works tomorrow. But usually this runs very smoothly, and you can look at the website. All the talks, which is over 60 talks already, they're recorded and they're all available on this website if you're interested. So thank you very much for your attention.
It's very interesting talk.
Thank you very much. Very nice. Concerning these exceptional points, when we arrive to the exceptional points, the spectrum splits, and now the eigenvalues are complex.
Yes.
Which is the physical interpretation for the eigenvalue for the imaginary factors? This work for non-PT-symmetric, but still only expected.
Non-PT-symmetric real potential, real energies.
With real energies.
Real energies.
Complex or non-Hermitian Hamiltonians.
Yeah, I don't actually know anything about this system. Yeah, very often people say, oh, this system is not PT-symmetric, but it has real energies. Yeah, I don't think you can say it's not PT-symmetric. Yeah, as I explained, PT-symmetry should not be taken literally in these circumstances. There needs to be an antilinear symmetry. Yeah, and there are lots of examples where people claim, oh, there's no PT-symmetry here. And deformed space-time. People say, oh, this is not, if you deform space-time is not PT-symmetric, that's incorrect. Yeah, because there is an antilinear symmetry. It's just not x goes to minus, y goes to minus, z goes to minus. Yeah, even the simple 2D example I showed you, it's sometimes people say it's a partial PT-symmetry. I also don't like this because there are even other ways to do that. You can even commute x and y. All you need is an antilinear symmetry. The argument of Wigner just uses antilinear symmetry. Yeah, so when people say, oh, this is not PT-symmetric, that's a meaningless statement because you didn't prove there's no PT-symmetry. They just didn't find it. Yeah, and not finding something doesn't mean it doesn't exist.
And so in optical systems, we have to work in the Schrödinger picture. So people usually construct these non-Hermitian systems by considering complex refractive indices. But what about a non-Hermiticity coming from the big kinetic, like for example in transversal magnetic fields. There are some functions from the position in the
Yeah.
first term with derivative. Do you know some?
Yes, in fact, the field theories I showed you, they have a non-Hermitian kinetic term. And we believe this is not a problem. Not our referee. But we believe this is not a problem because when you transform the system, the kinetic energy term is perfectly well defined. So this is, there are a lot of, I call them pseudo problems. They appear, oh, there will be ghosts and there will be all kinds of things if you have this type of kinetic energy term. But that's the same as interpreting in the, for instance, p squared plus ix cubed term, x and p as the observables. You can find the most absurd scenarios. You can violate Heisenberg's uncertainty principle, whatever. But this is because you pick the wrong observables. When you translate this properly, you pick the right observables, everything is well defined. And that's the same here. There are no ghosts, in my opinion, because you look at the problem in the wrong way. The equations of motions are incompatible. So you have an incompatible system. We could argue like this. When you transform it, it's all fine. So in that sense, I think there's no problem having non-Hermitian kinetic energy terms. But you have to make them Hermitian somehow. You have to find a way to transform. There's another way I also didn't talk about. You can destroy the hermiticity by boundary conditions as well. That's another way to do it.
Thank you very much.
All right. Yeah. Students, please don't be shy.
So my question concerns the last part of the blocking or the QST. Okay. So there is there always a state of minimum energy in the symmetry broken case?
Is there always? Well, in the cases we looked at, yes. There were always minima. We could always identify the vacuum. That's your question, right? Yes, we could. And there were many vacuum, symmetric and non-symmetric.
People in Zoom, we can hear you too. So if you have questions, you can raise your hand. So let's turn on your mic.
I think there
There is a comment. There is a comment from, I think that's probably Laura. They're just thinking. But
You're
and
welcome.
everyone is me. So more questions. Well, I have one.
Okay.
In slide 25, I caught my attention a phrase about well, it's gonna be a bit
25, yeah?
Yeah, sorry.
Oops.
And maybe
Here,
you don't understand, but caught my attention
Here.
this phrase
Okay.
that says sudden death of entanglement. So maybe I miss well, what does this phrase mean, or how is entanglement?
It's not my phrase, but but what if you do sort of mean field theory or whatever, and you analyze this, you would encounter an asymptotic decay, and what you actually observe is more rapid. That's the short definition of, in comparison to this mean field approximation, what you expect is more steep. That's what sudden death is. And death is, it goes to zero. Yeah.
All right.
So, and this is what we don't find here. Yeah. So, full direction. So this is the key here. Yeah. In the PT regime, yeah, it's also dying. It goes to zero. Yeah. And it's rapid. Depending on the size of the bath, it's less and more rapid. But these are This is splitting hairs. Yeah. But this is more extended. Yeah. This goes more away at the exceptional point. And here we call this now eternal life, right? It's no longer dying. This is finite. This is going to some asymptotic finite value. Yeah. So in that sense, that's the comparison.
All right.
The expression sudden death was coined by Jean Eberle. He's a famous physicist working on optical systems.
I see. Okay. So somebody else has questions? Yeah. Oscar?
Thank you. It's a more technical question about the soliton model. You mentioned that the solution you have considering with the soliton is X. So that you have the superposition in which you have one soliton, and so on.
Not a superposition.
Yeah, that's my point.
Yeah.
Can we see that? Because I remember as sum, am I right?
I did not show you. I showed you several systems.
Yes.
Which one? KDB or Hirota? KDB. Okay. So KDB is before. Yeah, but I didn't show you the multi-soliton solution. I mean, it's coming out from here.
Yeah.
I didn't show you the plot.
Yeah, I see.
But we have them. We have them.
Yeah. It's not a mistake. Yeah. Because in general, the way in which a soliton interacts with another soliton is mathematically a nonlinear superposition. In this way, you can take two solitons and study the dynamics and look at the as particles. Some
yes.
So I remember that there was some linear superposition, and that was my
No. I never did that. So let's make this straight. So if in this case, if I take this, I get the one soliton. Yeah.
The second line.
Yeah.
What is tau?
What tau is this parameterization. So U is this, and
It's not the solution.
no. Well, it's the solution of the Hirota bilinear form.
Yeah.
That's what tau is. It's called the tau function. But let's be clear. If I take a soliton, and if I take another soliton with some parameter alpha, the sum of these two solitons, this is not the solution of the equation. This is not the solution of the equation. The two-soliton, which comes from here, which we have to construct, this is one function. This is one function, and this one function will look like this. It looks like two solitons, but this is one function. And what you can have is you can have different scenarios. They move, right? So they move. And this might be faster than this one. So this overtakes this one. And when you increase time, then it will go into something like this. This is meant to be the same as this. They regain their shape, but something happens. Something happened. When they scatter, there's a little shift. So in the middle, when they scatter, it looks really wild. It looks like this, and then they separate again. But in between, so if you look at this distance here, this has changed. So there's either an advance or a delay, a time delay or a time advance, and this can be interpreted, as you say, we can interpret them as particles, as attractive force or repelling force, depending on what you get. So we calculated this. We calculated these time delays, and they are completely closed formula. And in this, so this is the standard soliton schedule. So this would be this solution over here. The two parameters alpha and beta being related to the speed and the amplitude. If we calculate this one, we get a three-soliton. You get something like this. And then again, at the end, this will regain the shape. And you have three shifts. You know? And this is a property of integrability, which is used in quantum theory. Yeah. So this, you may now think, dynamically, there could be a shift depending on all three, like a three-particle S matrix. It's an independent object. But integrability means all the shifts are sums of the two-particle shifts. And that's, in quantum mechanics, is the factorization of the n-particle S matrix. This is the quantum mechanical analog of what is called the Young-Baxter equation. Yeah. So if we have in quantum mechanics a scattering, this is a three-particle scattering like this. Yeah. All three, 1, 2, 3, they scatter at this point. And in a general non-integrable theory, that's an object you have to treat separately. Whereas in an integrable system, you can decompose this. This is equal, because of integrability, we can move this to the side, and it becomes the Young-Baxter equation, which is a non-trivial equation when you have backscattering. So the order of the scattering does not matter, and it's just an order of two-particle scatterings. So that's integrability on the quantum level, and on the classical level, this is reflected in the soliton scattering by the fact that these shifts, which by the way are related to the scattering matrix, are just coming from the two-particle interactions. So that's a crucial feature of integrability.
Right. Any other question?
Maybe you said it and I missed it, but the last part, can you break CPT thanks to the non-Hermiticity?
It's already not a property of the theory, because if it had CPT symmetry, it would be Hermitian. So what I wrote was modified CPT symmetry. So there were these i's in front and plus minus. So it's not standard CPT symmetry. If it was CPT symmetry, it would just be all Hermitian. So one has to look for different types of symmetries. And there might be more complicated ones. So we have very easy realizations, but I'm sure there are more complicated realizations.
So more questions? I think there are no more questions. So thank you very much.